So, good afternoon to everyone. I welcome all of you to the 52nd lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. I am happy to introduce today's speaker, Dr. Fernando Ferreira from University of Sao Paulo, Brazil. Dr. Fernando is not a new person to us. He has already visited a couple of times Bharathidasan University. During his second visit, he had stayed here more than around 10 days and delivered a series of lectures on complex systems. But in view of students, I would like to introduce his academic background. Dr. Fernando completed his PhD in physics in University of Sao Paulo in the year 2000. After that, an year he spent as postdoctoral fellow in the Institute of Theoretical Physics, people call it as EFT, in Sao Paulo, Brazil. And followed by this, he spent another year as a postdoctoral fellow in ICTP, Trieste, Italy. Then he joined as an assistant professor in the University of Sao Paulo, Brazil in the year 2016. Then he has been elevated to associate professor in the year 2019. And for the past 4 years or so, he was working as an associate professor in the University of Sao Paulo. Dr. Fernando is working in statistical physics and nonlinear dynamics with an interdisciplinary focus on health systems, ecology, economics, and physics. He has a wide experience in qualitative and quantitative methods for analyzing empirical data, as well as mathematical and computational tools, such as agent-based modeling, game theory, dynamical systems, in particular chaos theory and fractals, cellular automata, and data science. Dr. Fernando worked as a main coordinator in 2 projects and as a collaborator in several other projects. Dr. Fernando is teaching for the Bachelor of Medical Physics course and graduate programs in modeling of complex systems, as well as in the physics applied to medicine and biology. He has supervised graduate students working on agent-based modeling applied to socio-ecological and ecological systems, econophysics, nonlinear physics, and complexity. He has supervised more than 30 graduate students since 2010. Dr. Fernando is an expert in econophysics, and he has published a considerable number of papers in this interdisciplinary area of research. With this short introduction, now I invite Professor.
Thank you, Professor Sentil. I'm very happy to be here, and it's an honor for the opportunity to give this lecture for your department. Is a group that we know for more than 20 years. And I hope that I can motivate physicists to study topics in economics, because that I think that is an interface that will be a good opportunity for us as a physicist in nonlinear dynamics to contribute to this area. So the idea of my presentation is give this perspective, and in the end, I will try to show some example about what I'm talking about. So the outline of my presentation is the following. First, quickly, I will define or say some word about economic science. After that, I try to link complex system with economics, because I think that if a physicist want to work on economics, I think is good idea to have some history or some perspective to go into this topic, as in our case, for us, is an interdisciplinary interface between physics and economics that we call the econophysics. And After that, I will show one model that I'm working now. That is, I think, is promising in the sense the model is rich, and there is a lot of things to do in the perspective of nonlinear physics. And I will present results and conclusions. So let's start. Economics is the study of how society use scarce resources to produce variable commodities and contribute them and distribute them among different people. So everybody knows what economic is, but it's not. It's nice to point out or to remember you about the importance of economics in our daily life. So if you recognize that economics is very important and is not so far from what of our background as a physicist, I think we can open some doors and go in some model that will probably in the future solve a lot of issues that is open in economics. The ultimate goal of economic science is to improve the living condition of people in their everyday lives. Increasing the gross domestic product, for instance, is not a number of game. Is a very challenging problem that developed countries facing nowadays. So this is one issue that we could address in our model. Um, Also, economics is can impact in how allowed people to get higher incomes and has energy to warm houses, clean water, etc. So there is a many different issues that economics can bring to us as a matter of research. So the questions here is, may physicists contribute to advanced economic science? Is economics mathematizable as physics and chemistry? So I hope we can discuss this in the end, give some answer for this question. So I think the good way to address economics in the physics perspective is use the complex system idea or properties and try to explore them in economic models. So what is complex system? A complex system are system where the collective behavior of their parts entails emergence of properties that can hardly, if not all, be inferred from the property of the parts. So I highlight I did a short list of the main property of complex system. This list is not all. There are more items that we could include, but I think this is the essential. This is the important feature that we can take into account when we speak about complex system. The first one is emergence. So emergence, it's the next slide. I will go more deeply in this concept. But emergence is for sure present in all complex system. And after that, then self-organization, nonlinearity and unpredictability, numerosity. No, numerosity here means that a complex system is is uh, is characterized by a huge number of agents or elements that make part of the system. There is no magic number. We know it's a huge number. Heterogeneity. It means that agents may differ in some aspect. This is important. Adaptation and phase transition or bifurcation. So this is the topic that talk in the next slides. The first, in this slide, I will present two central concept in complex system: emergence and self-organization. It is not proven that they are necessary or sufficient property to characterize complex system. This is one problem we face here, that there is no consensus about how to define complex system. What we know to overcome this limitation is just evocate some good properties that is used to be present in the most, if not all, complex system. So here is the main one: emergence and self-organization. There is no theorem that proves that these two features are necessary sufficient condition to define complex system. But for sure, these two concepts are essential. What is emergence? Emergence is a collective property that results from interaction between parts. So since you see complex system as a collection of individuals or elements that interact with each other, so this phenomenon called emergence, it's just a property that emerged from the collective viewpoint. So this is a macro. It's observing the macro level. What is called attention is that emergent property cannot be inferred from the property of the interacting units. It means that if you know a lot of things about the individuals, you are not able to infer this emergent property that come out from these interactions. So emergence is something that is it's appear in the collective level, in macro level. It's not encoded in the micro or individual level. So it's property we call the emergence. Is in the ultimate word is fruit of interaction. Let me give an example. Here you see a brain, and in this brain is a set of neurons that are connected to each other, and this neuron is all the time change information. So the way they interact is through the signal they exchange one to others. So what's the collective behavior that is most striking, surprising in the brain? I can say now, for instance, the intelligence or the consciousness. So the intelligence is a property that is emergent. It's come from the neurons interaction, but we do not know how much neurons you need to have to emerge this property, and we even do not know how the intelligence depends on the neurons, but intelligence is there. We recognize this as something that come up from this neurons interaction. So the neuroscience is still in the beginning. There's a lot of things to find out and explain the future. So, but this is a very interesting example of emergence that is related to us, so we can experience this. There is many other example. For instance, vehicle in congestion cities, language and culture in human groups, stock market crashes are some example of emergent property that come up from different complex system. So on the other side, you see self-organization. So you can see some flocks of birds. I love this picture. And when you see these birds, that are able to produce a lot of patterns when they fly. It's a good, let's say, image when you talk about self-organization, because you see there is no one leader, and these birds are following some local rules, and through these local rules they reach some level or degree of organization. And this is remarkable. There are a lot of different complex systems that follow the same idea. Self-organization has to do with the order that we identify in complex system that also results from interaction rules that operate in the system in a decentralized way. So this is important word, decentralized way. There is no central agent that leads to increased order in the system, just local rules that drive the interactions. Flocks of birds, school of fish are classic example of self-organization. But we can add to the role of example the ant colonies that call our attention because they have a remarkable division of labors. More than that, if you look at the society, when people are mad with the government, for instance, they go to streets, what you call riots. Riots is also a kind of self-organization. Earthquakes, it's other phenomena that many countries experience. Is a example of self-organization. So a complex system is full of example of self-organization. And with the emergence, they play a very central role in the future definition of complex system. Um, another set of another concept that is I highlight in my presentation is the adaptation. Not all complex system is adaptive, but many are. Adaptive complex systems are widely studied because biological and social systems are adaptive. The main feature of an adaptive system is its ability to survive under change of environmental condition. So when we know that the environment is a change along the time, and when the system has this property to be adaptive, it's bring to some a certain resilience to the individuals to survive in different environment condition. There are several ingredients that's important to give the system this feature, what we call adaptation. In biology, for instance, variability in species, what we call the strains, is one strategy that evolution use to promote adaptation when the environment is changing. So here in the picture, you can see these bugs in several different colors, just to give an idea what we mean by variability. There's some feature, for instance, color of these bugs that made you fear, and this is some of these individual may be more interesting to avoid predators. So this is one example. The other example is or mechanism is for some animals, and we are among them, that have some cognitive ability. So we are able to process past information. We have a kind of memory, and we can learn from them. So learning is another strategy that is important to give to the system this feature of be adaptive. Here, there is a two other feature that is we are familiar as a nonlinear physicist. So nonlinearity that play important roles in chaos theory, and brings this feature of be unpredictable. And on the left side, you see some some figure that I think is nice, because it's exactly what's happening in the complex system. In complex system, we have two levels: the micro level, where individuals are interacting, and this interaction is you can see the network that link individuals or these nodes. These links are a proxy of interaction. Interaction means they are changing somehow information, any kind of information. It may be some electrical signal or gravity, or photons, or calling. Someone is calling money. So any kind of different way to change um, some signals or some material. It's a proxy of interaction, and this, when you see all these guys together, we identify some network, the network of interaction. So these interactions produce in the macro level some average quantity, some property that everybody are able to see. And this macro property, let's say some average of what people is doing in the micro level, will be able to influence all the guys in the micro level again, as we call what we call as a feedback loop. That is people or individuals or agents can react from what is happening when they have this global information, and they may change the way they are deciding, or they may react and change their behavior. And when they change their behavior, the macro also will be changed. So that is a feedback, and this feedback may be positive or negative. Let's give an example in econophysics. The price, the price formation. It's suppose there's some guy that is trying to sell or buying some goods. So each one gives some offer, they are able to pay some amount of money, and the other side, the seller accepts to sell if his expectative or this expectation will be attained. So they go to the market and they do some business. So after a round, the mean price will be clear for everybody, and someone pay above the average, some other guys below, and they may in the next round change the offers. Price will change, and this we produce a new mean value, and this is a kind of process that result in a price fluctuation. Price will fluctuate. Sometimes you see in the market, the people start to think that that asset is a good opportunity to get money, and they start to buy, and the price increase, and they still buy, the price increase, and this is what we call bubble. So you see some bubble in the market. So the bubble reach a certain level, and they start to think, no, now it's expensive. I think it's good to sell. And there is a synchronization process where a lot of guys sell the asset, and the price drop drastically, what you call crash. So this mechanism is nice because you have some fluctuation, sometimes bubble, sometimes crash. And the last feature I want to highlight is it's something that is very familiar to us. It's called phase transition bifurcation, and I do not need to say much because this is what we learn in physics schools. What I would like to do is just to remind you that phase transition bifurcation are characterized by the existence of a critical point that separates the system in two regions with different dynamic structure or behavior. So you have a critical point, and when you pass to this critical point, the system suffers some structural change in topology or in attractor, and this has a consequence. There's different way to classify this critical point: first order transition, second order transition, and recently in biology they start to study these bifurcation points, and there they call this as a tipping point. So tipping point is for physicists a critical point related to phase transition. So just to give an example, in biology, consider a very large forest. This forest is coupled to the local or the microclimate, and this coupling between forest and the microclimate drive the level of rainfall. This is what we see, for instance, in tropical forest. As we cut down the trees, deforestation process, this local climate may change. And suddenly, the attractor change, and without our interference, from a certain point, the forest will become extinct and turn into a desert. So this is the main problem when we see people cutting trees in forest. We do not know the amount of trees you need to have to avoid to pass through this tipping point or this critical point. So the problem is, once we there, we do not need to cut more trees. The nature will do this for you. So it's go to stitch. So it's very important to be able to quantify this critical point to avoid extinction and collapse of the system. So in summary, what we need to have in mind when we talk about the complex system is some feature that I listed here. Large number of agents. These agents may differ each other, and they are linked. They are networked. They change information each other, what we call the interaction, in a nonlinear manner and with feedback loop. Behaviors that come up from this interaction is the emergence, self-organization, and adaptive mechanism that's play an important role in many systems. And lastly, there's some criticality in several complex systems characterized by some phase transition or bifurcations or bifurcations. And one thing that physicists are interested in when they study this criticality is the scaling law or the power law that that we're able to measure in the end. So okay, now I want to link complex system and economics. So what my strategy was look at the property and the example in economics. So for instance, emergence. In economics, we see several emergent feature as inflation, depression, prosperity. So inflation is something that no one desires in economy, neither workers, neither employers, neither government. Everybody wants to avoid inflation, even though it's come up sometimes. So now the world is facing some inflation as a result of many factors. The main among them we can say, for instance, the Ukrainian war and the price of petrol. Yes. Self-organization, is easy to recognize in economics. The decision making is decentralized. Each player, each economic agent decide how much they want to pay, or for and how much want to pay for any kind of goods that in the market. No one controls this. This is the decision of the firms and the consumers. Non-linearity and unpredictability is it's a very common sense. We cannot predict the future of economy, and there is a lot of non-linear rules that govern the decision of economic agent. Numerosity is of course there. Economic is it's characterized by the presence of billions of agents. Heterogeneity, yes, there are many heterogeneity. Workers, employers, sellers, consumers. So the roles of individuals change, are different. And with if you focus, for instance, in workers, you see different kind of workers in the system. They are not equal. And adaptation, the capitalism is the system that is characterized by innovations and introduction of new technology. For instance, the internet, the artificial intelligence, robots, machine in industry, pesticide in agriculture, and the necessity of clean energy source transition for to avoid this climate change. So, of course, this system is adaptive. In this way, were able to link this complex system feature and economics. Now, I do something more specific. Let's go to a model where we can see how the complex is appear even in this macro and stylized model, this toy model that will be a pedagogical way to show how physicists can go through economics. So recently, I started to study what is called the Boali Model. Boali's model that was proposed or published in 1999. It's a model with three equations, three dimensions, with three variables, x, y, and z, which represent saving, GDP, gross domestic products, and the foreign capital inflow. So we have three economic variables in this model that is you can see in the equation one. So Bouali was very smart and very lucky because when he proposed this model, he start from two variables, x and y. X, if you drop from this system the variable z, for instance, you drop for a moment, this two equation in x and y is what physicists know as a van der Pol system. So in this van der Pol system, what we have, we know that there is a limit cycle attractor there. So this van der Pol are able to produce a kind of oscillation or oscillatory solution. And the oscillatory solution, it's is interesting for economists, because when you see a large windows of the economic dynamics, what do we see? Sometimes the economy is in the phase we call prosperity. The GDP grows, people save money, consumer is spend money, everybody's happy. So this process reach some limit, and the price and the GDP or the money start to decrease. So we go to a crisis. So this has some limit. So you have some fluctuation, normality, and prosperity start again, and crisis, normality, prosperity. So there's some oscillation, and Bouali realized that Van der Poel it's a very good model to produce a dynamic that remembered what this economists called business cycle. So this movement, prosperity, crisis, normality, and that repeat over time is what the economists call a business cycle. And these Van der Poel are able to mimetize this kind of dynamics. So what he did, he's introduced another variable, Z, that's related with the capital that the countries change with other country, the foreign country. So he introduced this variable Z, and then he looked at to the parameters, all the parameters, and he went to the economic literature to give some interpretation. For instance, B in the model is what economists call the value of the potential gross domestic product. The idea behind this parameter B is that if you want a model where there is no inflection, so you want to control, you want to fix the inflection, so the economists used to fix this um, the inflection through the parameter B. That means the potential, because if the GDP grows beyond a certain level, it's you cause inflection in the systems. So this model has some hypothesis that there is no inflection um, assumed here in this model. So Bouali went to all these parameter and map it with some economic interpretation, and that I list in this slide. So if someone wants to know more about the interpretation of each of the parameter in this model or the next model that I will present soon, I will let to you the reference in the end of my presentation. So this is not the main issue to know what the parameter means, but what's important here is that this system are able to produce the business cycle, and this was inspired by the Van der Poel system. So I presented this model to a friend, economist, and he looked at all these equation, X, Y, and Z, and he told me that in the Boali model, Y has some problem. First is that the dependence between Y and X is not the parameter -1, but we should put some parameter and let this dependence be more flexible. More than that, he told me that we should put some dependence in Y. So Y dot depends on X, Y, and Z. So what we did is we wrote the equations with dependence in Y, X, and Z. And this model, now given by the equation 2, is more compatible, more coherent with the macroeconomic theory. So this is a more general version. We keep the same interpretation of the parameter M, P, G that was in Boali model. And we just introduced, we went to the literature, we did the same as Boali, and realized that V is the marginal propensity to consume, and W is the proportion of saving, and C was already in the Boali model, no? That is the output capital ratio. So with this, we have now what we can say modify the Boali model, and we start to study this system. Let's see. First of all, the attractor. So in this modified Boali model, if you keep this set of parameters and you change initial condition, we saw that there are two different attractor. The green line is a limit cycle for a set of initial condition, and the red line are the some strange attractor relate to other set of parameters or initial conditions. Sorry, the parameter are the same; it's fixed. So here in the right side, I just give a zoom, so you can see that in fact this is look like a strange attractor. And we start to study the state space diagram between, for instance, GDP as a function of the international flow of capital. So this constant C in the model. Look that it's a very rich. When you saw this, it gave a surprise because look, if you increase C, let's see the color. So the color is black or dark color means you are in you have some limit cycle attractor, and light colors means that you have a strange attractor. So for law value of C, we have this strange attractor, so it's chaotic regime. So in a certain point, for instance, when C is 52, for some value of G, this there is a transition, a bifurcation to a limit cycle. And if you still increase C, sometimes you leave this attractor, this limit cycle attractor, go back to this strange attractor, and again you can go through this limit cycle and so on. So you know, when you choose some D value and you vary the C, you see many things happens. So it's a very complicated diagram. And the same, we change the parameter D again me. So now is the GDP as a function of the marginal propensity to save. And again, we observe a very rich and complicated transition that it takes place for different combination of G and M. And okay, this is this system when you see the dynamic of only one economy, it's remarkable and it's very rich in the point of view of a dynamical system. So now we decide to coupling. So let's couple two economy, two or more economies. So here, yes.
Fernando, shall I ask you a question now?
Yes.
Can you go back to the previous slide?
This.
So how can you interpret limit cycle and other attractors in terms of economic model?
No, limit. So now this is what it is first. Each of this point here, we have the Lyapunov exponent, lambda. So when this Lyapunov exponent lambda is 0, we look at the attractor. It is a limit cycle. What is a limit cycle? Limit cycle It's when you see in economics, we have this business cycle. So economy is some is when you see some economic variable is oscillate on time. So there's some oscillation in economy, and this oscillation maybe is behind this oscillation there's some limit cycle attractor. This is our interpretation.
Okay, okay.
So oscillation economy comes from some limit cycle attractor. This is what we suppose, and this is the reason why Bouali starts his model from a Van der Pol system.
Mhm. Okay.
Okay,
Yeah.
and we couple it. So the idea was, okay, let's put two or more economy. So we choose to put this we propose this diffusive coupling. This diffusive coupling, we are supposed that economy connecting in a ring. So it's from a ring. It's one very simple topology. It's not the best one, but to study two economy or three economy, I think is nice. If you want to study more economies coupled, I think it's better you change the topology. Okay, but for simplicity, we just propose this coupling, and we where this cup is nice because it's different. Zi plus one minus Zi is reflect the commercial balance between countries. Okay, so and this uh, Xi coupling can be this guy can be this parameter can be zero, or for instance when this is zero for one country, a one or different of zero for other, we have what we call unidirectional interaction. So we are able to study this master slave system. So one system can influence the other, but not vice versa. Or we can let this coupling be bidirectional. So one country can influence the other, and vice versa. So we have two possibilities here. So what we did was try to study the unidirectional and the bidirectional type of interaction coupling. So look here when this C is zero for both system. Okay, what we have for different initial condition, we choose one that were limit cycle, and the other one was a strange attractor. So we now once you start with this situation, this picture, we start to increase this parameter x, and when we increase, we see the synchronization. So it's go to a chaotic dynamics for both systems by synchronized. It's a full synchronization, and if you continue to increase this coupling, you see the orbit split. And so here you see now is a periodic attractor, and they are in antiphase. So it's this is for the situation where the couple is unidirectional. When this is bidirectional, the difference is when for a large value of this coupling parameter, the orbit is split, the dynamic is chaotic, and it's unsynchronized, though desynchronized. Okay. So this is just to show how interesting is this system and how it depends on the initial condition. So now, okay, what we did was let's see synchronization as a function of one parameter, for instance, GDP. So take the GDP, different value of GDP, and vary this coupling constant and see what's going on. So what we observed was synchronization for this coupling when the value is low. So less than, let's say, 30, you see synchronization, And after some value, we see that there's a transition to desynchronized phase. So here, the color bar is the variance between the orbits. So if the variance is zero, means that this orbit, one is coupled, one is synchronized with the other. But this the variance increase, we lose this full synchronization. We can have maybe this phase synchronization, but we went to this some example. We pick up some example in this diagram. We saw that this dynamic is after for a large value of this x parameter is not a phase synchronization, but is completely desynchronized. In this case, we look at the other parameter, we see something similar. It's not completely similar, but somehow it is. There is a value, there is a region where you observe a full synchronization, and there is a region of this coupling parameter where the system desynchronized. So maybe here I think here we see some phase for low value of C. We observe a phase synchronization. Is not completely synchronized, but there's some phase synchronization. And in the other situations, is not. There's no phase synchronization. It's completely desynchronized. And the same we observe for this parameter W. I think it's propensity to consumer. And here, for the variable R, something very interesting happens. Here, we have this region that with full synchronization, and this red color is a phase synchronization. So all these situations here, all this point here, means that the system synchronized in phase. And yes, want to ask something?
Fernando, again, I have one question.
Yes.
Is the parameters have what are the units of these parameters? Because some parameters you have fractional values, some parameters you have 20, 40, like that. For example,
yes.
epsilon parameter 20, 40, it goes like this.
Yeah, this what it did is this the x, y, and z, the variables, they have no dimension.
Yeah.
And we allowed the parameter vary in some interval. So this interval, this we do not analyze restriction in terms of the value of the parameter, because there is no dimension. We did not calibrate the model with the real data. So here we just vary parameter without worry about think if this is real. This makes sense in terms of economic viewpoint. Maybe there's some restriction in the value of the interval we may use to study the system. Maybe there's some restriction. We did not analyze this carefully, but it is a good question, Cynthia. I think we need to check it.
Okay, Fernando. Okay.
Thank you. And here is nice because here we observe complete synchronization and phase synchronization. I know why it's phase synchronization because I checked this several thousands of points. We plot the attractor to see this kind of synchronization. So in this model analysis, we saw very interesting behavior or phenomena that come out from the model that we study from the modification of Boali models. So the economic interpretation was done part of by Bouali and part for our group. And I think, okay, this model is not a perfect model to study macroeconomics, but I think is if you work hard with economists, we can improve and give a better version of these equations to try, for instance, calibrate the model and predict the future of economy. But what is nice here is that the system from the nonlinear dynamic viewpoint is extremely interesting to study. And there is a lot of question that is open because we just start to study this dynamic behavior. So we can ask you, for instance, what kind of um, bifurcation have? Help bifurcation or have many different kind of bifurcation. So how is the route to chaos? And I don't know. There's many questions we can address and try to answer from this to understand better this system. So this model, despite of having 80 parameters, it can be considered simple for to study economics, of course. For physicists, I think that 80 parameters is too much. But to understand economies are more complicated. So the way physicists is going to study such a system is trying to propose some time model. And for economy, I think this is a good time model. It is possible to address a standard model with more coupled economies. Okay, here, one direction we can improve our study is, okay, instead of you put all the economies in a ring, try to different topologies, like a small word or scale free. And answer the question I proposed in the beginning. Yes, the physicists can contribute to economy according to the complex system approach. So there's many issue in economics that we can study if you adopt this complex system approach. So if you bring the questions to our to what you are used to work in our daily life. For instance, try to analyze the attractor and study the different dynamic behavior and so on. And finally, we hope that this model can inspire new studies to investigate issues in economics and in political economics viewpoint in the context of the international relation. So I think there is a lot of questions that is not clear answered by economists, and you can contribute. For instance, you have two countries, and one country can influence the other one. So it's nice to know what kind of influence from the dynamic viewpoint, of course, one country can do in other country that is, let's say, a kind of master-slave relation, you know. So I think we can learn a lot if you will be able to find some model that can be validated by economists and that still have a very rich property and dynamic underlying to the model. So guys, thank you for your attention. And now it will be a pleasure to answer questions.
Thank you, Dr. Fernando. So now the session is open for questions, clarifications.
Okay.
Fernando, I have one more question. Is there any drawbacks of this model?
No, yes, there is a lot of, because this is a toy model. One of the drawback of the model is, okay, we start from this van der Pol. And I think it's this is a limitation because, okay, this kind of equation we see in the economic literature. But there is a lot of different macroeconomic equations that is not based on the van der Pol system. So we can change this model. There is okay, maybe there is a lot of different variables, economic variables that we do not take into account. This is a limitation. And we okay, we what we did, it was not, maybe I forgot to mention what I went to the economic literature, and I saw some empirical results in this paper of Sella and Hanna. They have observed this business cycle synchronization. So we have some qualitative agreement between empirical and these theoretical results. But of course, we need a better model to at least to try do some prediction. I think we are not able to do some prediction now. So this is one limitation that we would like to overcome.
Normally, in economics, models are described by stochastic equations, right?
Yes. This is another. Yeah.
This is different.
You could try to put some noise here, or write down a stochastic version. This is something that is able also. Thank you to remember,
But this is a nice equation.
Yes, but but we'd like to this the deterministic approach, because you can do some analytical calculation and extract more. I think it's now we start to do some analytical treatment and analysis of the system. We just started this, and the next version of this study, we would like to put this. What would like to, for instance, we'd like to describe the type of the kind of bifurcation that come up from this model. I think there's several different kind of bifurcation behind. Depends on the set of parameters.
Right. Okay. So questions from students or others? Are any clarifications?
Guys, feel free to make any kind of questions. So because this is maybe my presentation was very quickly. No, I did not go to all the details. So
I think students are a bit hesitating.
Okay.
Are any clarifications? Okay, Fernando. Since there are no more questions, shall we conclude the session?
Yes. So thank you again.
So since there are no more questions, I would like to conclude the session by thanking Dr. Fernando by giving a. I think Murugananda wants to raise some questions.
Oh, Anand. Hi, how are you?
No, it's not question. Just
Okay. So I would like to thank Dr. Fernando for giving a very interesting talk on economic models. I learned a few things. Thank Thank you, Fernando. Thank you.
Yes.
Yeah, the students may write to you by asking some questions.
Yes, feel free to write. And again, Sentil, thank you very much for inviting me to this lecture, and I'm very glad to share with you these results we are studying recently, and I'm very happy to come here.
Thank you, Fernando. Thank you.
Welcome.
Thank you very much.
Bye.
Bye, Anand. See you.